All right, good morning. We're on chapter 7 notes. I did post these to Google Classroom. So if you would prefer, you can print them out and write on them, or you can copy them down and use that instead. It's up to you. Probably it will be easier just to print them out. All right, this chapter, what is chapter 7 about? We're talking about scatter plots, association, and correlation. So it says this chapter is about bivariate, that means two variables, quantitative data. All right, we should know the difference between quantitative and categorical. So quantitative, like height, weight, shoe size, income, hourly wages. These are all quantitative data. Calories, grams of fat. Categorical data, right? This is not for a scatter plot, so only quantitative. Examples of this would be the number of years of education and yearly salary. So this is two variables, right? So we've got the number of years of education, and yearly salary. That would be one example. Another example would be height and weight of adult men. So height and weight of adult men. Another example would be your age and the number of words you read per minute. We display these kinds of data on scatter plots, where on a scatter plot where the independent explanatory variable is x and the dependent or response variable is y. So again, independent variable or explanatory variable is x, and the dependent variable or the response variable is y. All right, so some vocab that we need to cover. A scatter plot. A scatter plot shows the relationship between two quantitative variables measured on the same cases. So what is a case? Like people, right? So like the height and weight of adult men, the height and the weight are for the same adult man. All right, association. So there's three things that we talk about in an association. We talk about direction, form, and strength. So DFS, direction, form, and strength. Direction. So the direction is positive or negative. So as one variable is increasing, the other one is increasing, or as one variable is increasing, the other is decreasing. So the direction positive or negative, or none. It could be none, right? It could be that there's no direction. So positive implies as x increases, y increases. And then negative would be as x increases, y decreases. Whoops. This is why I have white out. Y decreases. Our direction, form. The most often form that we're talking about for form is linear or nonlinear. So is it linear or nonlinear? And then finally, the last one, strength. So the strength The strength of the association is strong, moderate, weak, or there could be no strength. It could be very uncorrelated. And to find how strong it is, you look at the tightness of the cluster. And you also look at the R value. And we'll talk about the R value more in just a minute. Okay, an outlier. An outlier is a point that does not fit the general trend of the data. So an outlier does not fit the overall pattern. I should say it's a point that does not fit the overall pattern of the scatter plot. Response variable, explanatory variable, X variable, Y variable, right? So response variable is your Y variable, and explanatory variable is your X variable. So in a scatter plot, you must choose a role for each variable. And so you would assign the y-axis to the response variable, and that's the one that you're trying to predict. So I'm going to go ahead and for y, we're trying to predict this variable. And for x, our x value is the predictor variable or the explanatory variable. Explanatory, right? And I'll give you an example. If we were looking at these three examples up here, right? The number of years of education and yearly salary. So the independent or explanatory variable would be the number of years that you go to college. What we're trying to predict is if the number of years of college somehow increases or decreases your yearly salary. Why? Height and weight of adult men. Well, height, again, it's an independent variable. There's very little you can do to control your height. However, there's things that can be done to control weight. So Y, we think, is the response variable. Our height predicts our weight. And then age and the number of words read per minute. Again, I believe the older that you are, right? And I'm talking about maybe in, say, from the ages of, say, 3 or 4 to about the ages of maybe 16 or 17 or even 20. Your age, as your age increases, the number of words you can read per minute, Y, would probably increase. And so we think that this is the independent variable. The one we can't control is age, and the one that we could control or change would be the Y value. All right, correlation coefficient. So this is like the meat and potatoes, and you've probably heard this phrase before. A correlation coefficient. We use the letter R to represent that, and earlier I said R value, right? So your correlation coefficient is the numerical measure of the direction and strength of a linear association. So the numerical measure of the direction and strength of a linear correlation. So some rules about R. So first of all, R has to be a number between -1 and +1. So the closer to -1 and the closer to +1 that a R value is, the stronger it is. If R is 0, we call it no correlation. Now I'm doing absolute value here because I don't care if the value is positive or negative. If the absolute value of R is somewhere between, say 0 and 0.5, we would consider this a weak correlation. Now these are guidelines. These are not like hard and fast rules, okay? But they're guidelines that help students to make a determination. If the absolute value of R is somewhere between 0.5 and 0.75, we would call this a moderate correlation. And then finally, if the absolute value of R were somewhere between 0.75 and 1, we say this is a strong correlation. All right, and so anytime that the R value is positive, so if R is positive, greater than 0, we have a positive correlation. That means going back up to our notes up here, right? Positive or negative, it's as X is increasing, Y is increasing. And then if R is negative, right, then we have a negative correlation, and as X is increasing, Y is decreasing. All right, lurking variable. So a lurking variable is a variable that simultaneously affects both variables. A third variable that simultaneously affects both X and Y. So let me give you an example of that. So let's say that X is the number of televisions per capita in a country. And let's say that Y is the average lifespan in years. So if you could picture this, countries with a higher number of televisions per capita have a higher average lifespan in years. But that's only because there's a lurking variable. And the lurking variable here would be economic status. Right? It's a lurking variable because it affects the number of TVs that people could have. They have higher economic status, they own more televisions. And it also affects the lifespan in years because if you have a higher economic status, you're likely to have a higher healthcare industry and more access to it. Okay, so that's an example of a lurking variable. It's also a confounding variable. So some books will call a lurking variable something different than confounding. Confounding. Ours does, but it's actually been now for AP reasons, right? They call lurking and confounding pretty much the same thing, okay? Okay, so identifying correlations between data sets. So a correlation is a relationship between data sets. You can use scatter plots to describe the correlation between data. So here we have positive. This is something, this would be a nice strong correlation. The data points are really tightly gathered. So this is a negative correlation, right? As X is increasing, Y is decreasing. Again, strongly, right? The points are very tightly clustered. And this would be something that we would call no correlation or very little correlation. There's no linear pattern. The points are just kind of gathered. Now there's other examples of correlation, I'll give you a third example. So you could have something that resembles for example, a quadratic. So this is non-linear. Linear, and you describe it if you know it. So if you can recognize it as being a quadratic, you could say it's non-linear / quadratic. If you don't recognize the pattern, then don't say what it is. Another example of non-linear, you might have something that looks like a exponential or logarithmic. This one would be exponential, right? But we would just say this is non-linear. But regardless, these data points are tightly clustered, so they would still be strong. Okay. But mostly what we deal with in AP Stat is scatter plots that are fairly linear. So when a straight line provides a reasonable summary of the relationship between two numerical values, we say that the two the two variables are linearly related, or that there's a linear relationship between the two variables. All right, let's go ahead and flip it. So for example, below are 3 scatter plots. The scales on the X and Y axis have been left off, so you will have to think carefully about the relationships. So they're calling this Y1, right, scatter plot 1, this is scatter plot 2, and this is scatter plot 3. So they're identifying those for you. If one of these plots represents the relationship between height and weight for 8 adults, which scatter plot do you think it is and why? So I would assume that as someone's height increases, their weight increases. It would be very unlikely to find a woman who's 5'2" and weighs, say, for example, 400 pounds. Most petite women weigh less. Now, of course, they could be overweight, so they could increase their weight, but in general, if your height is shorter, you tend to weigh less than someone who is equally thin looking who is taller. So if I were to pick one, I would say A, or 1, I'm sorry, there's no A, my bad. I would say scatter plot 1 because in general, shorter people tend to weigh less, and taller people tend to weigh more. Now, in AP Stat, there's a very specific way we say this, and we'll get there, but I'm going to say it out loud. I'll write it later, but for right now, we would say, in general, as height is increasing in feet or inches or whatever the units are, weight tends to increase or is predicted to increase, the weight in pounds or ounces or kilograms or whatever metrics we're using. Okay, if one of these relationships between height and SAT math score, represents the relationship between height and SAT math score for 8 seniors, which scatter plot do you think it is and why? So if I think of someone's height and I think of their SAT math score, and they're all seniors, right? So it's not like, oh, you got freshmen through seniors, where as you get taller, you're getting older. So your score could be improving because you're taking more classes. We're looking at only seniors. So if I were to predict that, I would say I don't think there's any relationship. So I would call it scatter plot 3. Among seniors, there is very little relationship between height and math scores. I don't think being taller will influence someone's math score. All right. Next one. Well, by default, right, we're going to say this has to be plot 2. But let's check it. If one of these scatter plots represents the relationship between the weight of a car and its fuel efficiency for 8 cars, which one do you think it is and why? So now let's think about this. As the weight of a car increases, it's heavier, it takes more power to pull it, which means that the fuel efficiency will go down. And so it should have a negative correlation. So as X is increasing, Y is tending to decrease. Again, I'm going to say this in words. As the weight of the car in pounds increases, the average fuel efficiency in miles per gallon tends to decrease. All right, so because in general, heavier cars tend to use more power and therefore more fuel. Okay. All right, moving right along. Describe the association of each scatter plot below. So when they say describe, we're doing what we were talking about right here. Association. We're describing the association. We need to talk about direction, form, and strength. So the first graph, scatter plot 1, I notice that there's a general downward trend, which would imply it's negative. It is roughly linear. I can kind of see a linear pattern happening. But the data is not gathered very strongly. So I would consider this for direction, D, right? I'd say negative. For form, I'd say linear. And for strength, I wouldn't say weak. I would say it's somewhere between weak and moderate. So they're not going to ding you. For sure, we would not call it strong. We've got these 2 points down here that kind of make it not super clustered together. So weak or moderate, they're not going to ding you. Now, in a full sentence, which there's not a ton of room here, so I'm going to say it. This is age in years, and this is number of cell phone calls. So I actually will write it. I'm going to squeeze it in up here. There is a moderate negative linear association between age in years and number and predicted number of cell phone calls. All right, this is the AP Stat interpretation. When they say describe it, they don't want negative, linear, moderate. They want you to say there is a moderate negative linear association, or you could say a moderate linear negative association between age in years and the predicted number of cell phone calls. Scatter plot number 2 does not look linear to me. I'm going to look at the units. So this is frying time in seconds, and this is, oh my gosh, hold on, let me look at it. Moisture content. Okay, in percent. All right, moisture content in percent. So this time I would say that it's a nonlinear, it looks like exponential decay to me, right? So I would say my direction, D, my form, F, and my strength, S, I would say that there is it's negative, nonlinear, and the strength, again, I would call it moderate relationship or association. So this one I'm not going to write out, but you need to write it out. I would say there is a moderate, negative, nonlinear association between frying time in seconds and predicted moisture content in percents. All right, go ahead and do that. If you need to pause here, pause it. I'm going to move on to the next one. Now this one, it doesn't seem to me that there's any relationship. Let's see, my X variable is, let me pick it up, I can't see it. Price in dollars and quality rating. I'm sorry that these are so tiny and hard to read, but right, I'm doing my best, guys. All right, so price in dollars and then quality rating, we don't know of what, so we can't really say. But my direction, I would say that there's no direction, none. It's not increasing nor decreasing. My form is none. There's no form to it, none. And my strength, again, weak or none. Very unlikely you'd get a question like this and be asked to describe the relationship. Okay? And then finally, this one almost looks quadratic. If it weren't for this point, right, it wouldn't, but it does look quadratic. So my direction, there is none, right, because there's negative and positive, so no direction. My form would be quadratic, but it would be sufficient to say nonlinear. And my strength, I would call it, well, it's fairly strong if you look at a quadratic. So I would say moderate to strong. And either would be correct. And again, the whole idea here, guys, is that it's very unlikely, particularly since we're only going to have 2 questions on the AP exam, that they would give any kind of regression that was anything other than linear. So we're going to focus on linear and how to describe a linear association. All right. Let me see. I think that's the end of this chapter. I'm just double checking. Yeah, so there's a few things that we're going to add into our notes. These are like the general notes. So we're going to add a few more examples, but for right now, that's pretty good. I'm going to pause the video here and then we'll have a part 2.